Hi friends, uh, in this YouTube video I want to discuss about MHC proteins and HLA matching. These are some parts of the immunology which we seldom understand better, and we usually tend to ignore these topics and used to cram over our books one night before the exam. But I would honestly say they are highly conceptual things which are extremely important in understanding the immunology better. So let's get started with MHC proteins. So MHC, we all know MHC is abbreviated as major histocompatibility complex. So as we know, these are the proteins that are present on the cell surface. MHC1, which is present on all cells of the body, all nucleated cells of the body except RBCs, but platelets do have it, and MHC2, they are present exclusively on the antigen presenting cell. So what is the requirement of these MHC molecules? Here I would like to quote that MHC molecules are individual specific antigens, be it MHC1, 2 or 3. I would like to say MHC molecules are individual specific antigen, means they are particular to a particular individual in a given species. Means nor your MHCs are similar to mine, nor mine are similar to my neighbors. We do have MHC matching with our parents, but that is maximum up to 50%. Okay, we match up to 50% of our MHCs with our parents, not more than that. So MHCs are something which makes an individual, it provides an individual his individuality in the form of individual specific antigens. So these MHC proteins are hence coded by a gene, HLA gene, present on chromosome number 6 of every individual. I would like to repeat again, HLA genes are present on chromosome number 6, which code for MHC proteins, which are extremely essential for providing an individual its individual specific antigens. So since these antigens are dear to any individual in providing him his individuality, these proteins are basically used or basically present in the body to identify something foreign that enters in our body. Yes, they are potentially the antigens or the proteins that recognize the foreign invaders. So they have the major function in identifying a foreign antigen presenting to our immune system and development of immunity, and they are also essential in recognizing a foreign antigen which comes into our body in the form of transplant. So MHC molecules are required for two roles, that is, they recognize the foreign antigens in the form of pathogens and mount an immune response against it, and they also recognize a foreign antigen in the form of a graft or a transplant inside the human body. Since these molecules are highly vital molecules, we should know something about how many types are existing for MHC molecules and what are their individual functions. Continuing our discussion, I would like to say MHC molecules are of three types. There are three types. On chromosome number 6, HLA gene has 3 loci that codes for 3 different types of MHC molecules. It is a schematic diagram I have made which represents the different loci for different MHC molecules. So MHC1 molecule has 3 loci, namely A, B and C, which are present on the gene as single loci A, B and C. MHC2 molecule, likely it has 3 loci, DP, DQ and DR, which are also present on chromosome number 6. Now MHC3 molecule is less important to know in the UG curriculum, but it is a complex locus that has many regions that code for different functions of our acquired and innate immune responses. Among these three MHC molecules, important to us are MHC2 and MHC1 that are highly essential in activating our acquired immune responses, mounting a strong immune response against a foreign invader as well as a transplant. To remember the loci of MHC2, I would give a simple trick. 2 means each locus has 2 alphabets, namely DP, DQ and DR, and similarly 1 has 1 alphabet in each locus, A, B and C. So let's now learn what are the functions of each MHC molecules. So to be precise, MHC2 molecule helps in recognition of exogenous antigens and presenting it to our T helper cells. T helper cells help the immune response to ward off the exogenous antigens. And MHC1 molecules are highly essential for presentation of endogenous antigens to cytotoxic T cells or the killer T cells that kill the endogenous antigens. Before heading forward, I would like to explain what are these exogenous antigens and what are these endogenous antigens. Exogenous antigens are something that come from outside the macrophages or the phagocytic system. Phagocytoses them and prepares a protein fragments that belongs to the body of the organism. So when a foreign invader or a foreign agent is phagocytosed and is broken down into small protein fragments, they are called the exogenous proteins. But endogenous proteins are those proteins that are synthesized inside our cell. It can be an intracellular organism, an obligate intracellular organism like Mycobacterium tuberculosis, or a facultative intracellular organism, that is, organism which is usually extracellular but has the potential to grow and replicate inside the cell. Viruses and fungi, intracellular fungi, and even tumor cells that produce their own antigens inside by living inside the host cell. They are called the endogenous antigens. So endogenous antigens can be self antigens that have mutated, example tumor genes, or can be obligate or facultative intracellular organisms, viruses, or even intracellular fungi. Now, MHC2 molecules are therefore, since they represent the exogenous antigens, they are present on antigen presenting cells which are potential phagocytes also, that is dendritic cells, macrophages and B cells, whereas type 1 MHCs, they are present on all the cells of the body, all the nucleated cells of the body except RBCs and including platelets also. The MHC1 molecules are present on all the nucleated cells of the body including platelets, but they are absent on the RBCs since they have the potential role in displaying the endogenous antigens and the virus or the bacteria or the invader cell where they can potentially grow and invade depending upon their specificity. Now, coming to the structure of the MHC molecules, first I would like to describe the structure of MHC1 molecule and correlate how they correlate the genetic loci with the structure of the MHC protein. Now, the structure of MHC molecule MHC1. MHC1 is a polypeptide of alpha chain. It is an alpha polypeptide. We have named the polypeptide as alpha and have divided the alpha polypeptide into 3 regions: alpha 1, alpha 2 and alpha 3. And the beta 2 microglobulin, it is a non-MHC. It is a non-MHC protein that has a locus on chromosome number 15, and it is non-covalently bound to the alpha chains to stabilize it. Okay, it has the major role in stabilizing the MHC1 molecule. So the genes HLA-A, HLA-B and HLA-C, they secrete different types of alpha chains, and the alpha chains of each MHC molecule are a permutation and combination of the different peptide sequences that are synthesized by HLA A, B and C respectively, and the folded chain of alpha 1, alpha 2, alpha 3, they are the different permutations and combinations of HLA A, B and C genes, and MHC1 genes are highly polymorphic. That is, they can synthesize MHC1 molecules of different kinds. Okay, near about 1500 different MHC genes can be MHC molecules can be found by a single gene, and they have specificity for a wide arena of 1500 different antigens. Now, the alpha 1 and alpha 2 pockets of MHC1 molecule, alpha 1 and alpha 2 pockets, alpha 1 and alpha 2 pockets, they have a pocket between them, which is the antigen binding pocket, and MHC1 molecule can bind to antigens of size 8 to 10 amino acids of length. Alpha 3 fragment is a transmembrane fragment that enables the existence of or adhesion of MHC1 molecule on the cell surface. As I have already said, beta-2-glycoprotein is a non-MHC protein that is coded by a gene in chromosome number 15, and it stabilizes the MHC1 molecule by covalent, non-covalently binding to alpha 1 chain. So this is all about the MHC1 molecule. Now coming to the structure of MHC2 molecule. MHC2 molecule, it has a gene, HLA gene on chromosome number 6, and it has 3 loci, DP, DQ and DR, and each locus codes for 2 different types of proteins, that is alpha and beta. So MHC2 molecule is a heteropeptide of alpha and beta chains that are stabilized by the disulfide bonds, among which the alpha chain has a variable part and constant part, and beta chain has a variable part and constant part, and both of them have a transmembrane part to stabilize them. And the alpha and beta chains are different permutations and combinations of peptide sequences synthesized by the DP, DQ and DR genes respectively, and this permutation and combination provides different antigen specificity to this heteropolypeptide, that is the MHC2 molecule, and the antigen binding pocket is found by the alpha variable and beta variable parts of the MHC2 molecule, which can bind to peptide antigens having 13 to 20 amino acids sequences. So they can bind to polypeptides, and the MHC1 can bind to oligopeptides having 8 to 10 amino acids. So we have discussed about the major histocompatibility complex, on which genes they are present, what are the different types of major histocompatibility complexes, where the MHC molecules are present in our body, the structure of MHC molecules in brief, and let's now know something about the HLA matching. So HLA matching is something that most of the students do not understand, and in UG, in my case, actually I didn't understand in my second year what is this HLA typing and HLA matching, I just crammed it up a night before exam, and hopefully luckily I didn't get any question, and I was not asked in the Viva mostly. So it's understanding, and it is essential in understanding the host versus graft rejection, host versus graft reaction, and graft versus host disease, that are potential questions in the patho exams of the second MBBS. Now, HLA matching. HLA, as I have already said, that HLA genes code for the MHC, major histocompatibility complex proteins, that are the individual specific antigens present on the cell surfaces of a given individuals of a given species. Neither of the two individuals have same HLAs, provided they belong to same family and share the same gene pool. And in the family, even the first degree relatives, they also do not have the same HLA matching. Now, I would like to use the Mendel's Mendel's crosses basically to make you understand the HLA matching between a child and its parents and child and its siblings. Suppose a child X, progeny X, has parents, father, mother, who have, and father has X1 and X2 genes. Father has HLA genes on his 6 chromosomes, and since we are diploid organisms, father has 2 6 chromosomes, and on each 6th chromosome there are 2 HLA genes, X1 and X2. Similarly, mother has 2 HLA genes, X3 and X4, on her chromosome number 6, and she has a pair of 6th chromosome. Now, there are the possibilities of HLA genes in the progeny are X1 and X3, X1 from father, X3 from mother, X1 and X4, X1 from father, X4 from mother, X2 and X3, X2 from father, X3 from mother, X2, X4, X2 from father, and X4 from mother. So, in all these instances, we can see that progeny has no chance of getting the whole HLA of father or whole HLA of mother, since it's a dihybrid cross. Okay, so in each genotype we see there is 50% similarity of the child with each parent, that is X1 50% with father, X3 50% with mother. In all instances we see, all instances there is 50% matching between the child and the parents. So we do not match, our HLAs do not match 100% with our parents. Okay, that is why it sometimes becomes cumbersome in getting organs. Second, the possible, let's see the HLA similarities between siblings. Suppose the child is born with HLA type X1, X3. Let's now see how much does he match his genotypes with his siblings. The siblings have genotypes, suppose X1, X3, X1 or X4, X2, X3 or X2, X4. And now the progeny, first progeny has, or the first child has X1, X3 genotype, and his siblings can have all one among these genotypes. So the first genotype, possible genotype of his sibling X1, X3 completely matches with him. So it is 100% matching. X1, X4 matches 50% with it. X2, X3 matches 50% with X3, and X2, X4 doesn't match at all. So if the child has 4 siblings, 3 can have matching, some degree of matching with this child. So there is 75% of siblings have similarity, and only 25%, 1 among 4, can have 100% similarity of HLA with his sibling, with his elder sibling. So not only monozygotic twins but dizygotic twins, even siblings can have 100% HLA similarity, and the rest too can have 50% similarity with the first individual. Therefore, and moreover, the mother who has nurtured the child for 9 months in her womb can develop antibodies against the child while the umbilical cord is cut and the blood mixing occurs. So it is not safe to procure an organ for a child, for a individual from his mother, because mother can have developed antibodies against this child who has 50% mismatching with the mother also. And since we have already seen the siblings can even have 100% similarity with each other in terms of HLA typing. So during organ transplantation it is best to receive a graft from sibling, provided the individual has not developed any antibodies against his sibling in the form of previous blood transfusions, and it is wise not to receive blood transfusions from first degree relatives. Okay, but blood transfusions that do not have leukocyte or leukocyte depleted blood transfusions are safe to carry out, because RBCs do not have MHC proteins on them. So thank you. That's all for today's video. I hope you like it, or whatever flaws are there you can comment on the comment section. If you have any doubt you can also ask in the comment section also. And thank you so much. This is my first attempt after all in making a YouTube video, because in this quarantine I was really getting bored. So I hope you like it. Thank you so much. Namaste.